This question is from GATE 2021 Mechanical Engineering paper, set 2, question number 38. A spot welding operation performed on two pieces of sheet yielded a nugget with a diameter of 5 mm and a thickness of 1 mm. The welding time was 0.1 second. The melting energy for the steel is 20 joule per millimeter cube. Assuming the heat conversion efficiency as 10%, the power required for performing the spot welding operation is dash kilowatt. Let's find out. Let me start by enlisting the given things first. Diameter of the resulting nugget is 5 mm. Thickness is 1 mm. Time taken for melting is 0.1 second. The heat required to melt is given to us, HM, which is 20 joule per millimeter cube. Heat transfer efficiency, eta H, is given to us as 10%, and we need to find out the power required to melt. So this power required to melt will be given by the heat input required, HI, into volume of the nugget upon the time required to melt it. Because the resulting nuggets have the same volume as the two pieces of the steel that is used to produce them. So volume of them will be taken as V itself. This is actually the volume of two pieces of steel which are being melted, which is equal to volume of nugget. So we know that V can be calculated easily because diameter and thickness are given to us. So it's a cylindrical geometry and volume will be given by pi by 4 d square into the thickness H. HI, the heat input required, we don't know yet because we know the heat that is required for melting, which is available for melting, which is the output heat energy divided by T. So when we write it in terms of efficiency, we have total efficiency, which is efficiency for melting, into heat transfer efficiency, eta H. It will be equal to the output value, which is nothing but HM, heat required to melt the two pieces of steel, divided by HI, which is the heat input required. Because it is a spot welding operation, these two values will be different. So what we are given is this value, heat required to melt, and what we need to find is the heat input required, HI. Now eta H is given to us 10%, eta M is not available. So we can assume eta M as 100%. Because it's an efficiency value, we don't have any idea of how much to assume. It's not given to us, so we can say that it's 100% efficient. Therefore, eta M can be written as 1 into eta H is 10%, which can be written as 0.1 in the form of number, will be equal to HM is given to us 20 joule per millimeter cube divided by HI we don't know. So rearranging this, we have HI equal to 20 upon 0.1, which is 200, but unit here is joule per millimeter cube. So this is energy per unit volume, and that is why we are multiplying volume here while finding power. So substituting the value here, we will have HI is 200 as we found it out, into pi by 4 into d square, which is 5 square, into H is 1 millimeter itself, divided by time is 0.1 seconds. We are not converting any of the values of the geometrical measurements because this value is per millimeter cube. So we are multiplying the diameter and thickness value in millimeter itself, so as to get the power in joule per second, which is watt. So this, when calculated in the calculator, gives us power as 39,269.9 watt. We are being asked the answer in kilowatt, so just dividing this by 1000, we have the power value as 39.2699. So rounding it off to two decimal places, it is 39.27 kilowatt. Let's go back and fill in this answer. So the power required for performing the spot welding operation is 39.27 kilowatt. We have already rounded it off to two decimal places. To learn more about resistance spot welding, you can refer to the NPTEL video, Resistance Spot Welding Part 1. It's from the course Welding Processes. The course is by Professor Murugaiah Amarthalingam. He is from Department of Metallurgical and Material Science Engineering of IIT Madras. I hope this solution helps you clear your doubt. Thank you.